Swayam Prabha. Digital India. Educated India.
I'll just continue with what Professor Paulo has started. Of course, the course is on additive manufacturing of ceramic materials. So it's a relatively new manufacturing technique, and hence we are all very much interested to learn how to print ceramic materials. Unlike metal printing, ceramic printing is always not so easy. It comes with a lot of issues. Nevertheless, it's a very interesting topic, and therefore we are here. But as engineers, one of the most important aspects of manufacturing technology, when you develop a new manufacturing technology, we always look at, as engineers, we always look at the properties of those materials. And unless these properties of materials are clearly understood, and as material scientists, unless we correlate with its microstructures, we cannot really qualify them, and they really will not see industrial use. So therefore, it's very, very important for us. Whenever a new manufacturing technique is established, we always look at its microstructures, and subsequently we also look at its properties. And for most of the applications which are load bearing, mechanical properties of materials becomes very important. Of course, depends on the application. If you're talking about applications which are functional, possibly mechanical properties of materials may not be that relevant. But all ceramic components, irrespective of whatever manufacturing technique that you would have used, including additive manufacturing, if it has a load-bearing application, understanding its deformation behavior becomes very important. And that's the reason why I'm just taking 1 hour. Although you have come here and registered for additive manufacturing, and so I would like you to know more about additive manufacturing. But nevertheless, I think areas such as this are very attractive, but we also have to live in reality and see whether a certain technique, however novel it could be, whether it would be industrially viable, whether we can really take it to applications. And therefore, I will take just 1 hour talking about mechanical properties of these materials. So when you talk of mechanical properties of materials, obviously we need to know and understand how do we do this testing. So obviously testing techniques cannot change. Whether your manufacturing techniques can change, but testing techniques cannot change. Maybe it can get modified depending on the size of the samples, but the testing techniques cannot change. So whatever mechanical testing techniques I will talk today is something which you may be already aware of. But I still feel that it is important to emphasize, because many times what we think we know, but it's important to know it much better so that we understand to use these techniques for the kind of material systems that we are working on, and as well as for the techniques that we have used. So disclaimer is you may have known this, but still nevertheless it's important to quickly review it. Of course, if you have any questions, please feel free to stop. Why are we interested in this? We are interested because new manufacturing techniques enable us to look at applications. At least again, as engineers, we always look at applications. And one of the prominent applications that we are currently looking at is use of these advanced ceramic materials for various applications. Automotive, it could be automotive, it could be aerospace, it could be semiconductor. So these are 3 very vital applications that we generally look for using ceramic components. And obviously, we are also looking at newer techniques, because unlike again metals, it's not so easy to machine them. It's not so easy to make complex shapes, but many of the applications may require complex shapes. So therefore, additive manufacturing hence is a very interesting technique. So anyway, nevertheless, let us look at, for example, where all ceramics can be used in automotive applications. And now if you look at as we are moving closer to electric vehicles, if you take an electric vehicle in an electric automotive application, you can think of several applications, right from lightweighting, for example, lightweighting such as using say silicon nitride balls, using them for bearing applications, removing completely steel balls, so that you have lightweighting. Two, for example, sensors and many of the electronic components and of course battery components require ceramic materials. And obviously many of these ceramic components are not very straightforward. First of all, right from chemistry, making these materials and fine tuning at the chemistry level too, manufacturing them becomes a very relevant issue for us. So I think this is something that we should be aware of, that ceramics are now found applications extensively in electric vehicles. And one of the major manufacturers, I am sure you would have heard, Tesla, is one of the major companies which uses technical ceramics extensively, as opposed to other companies like Ford. Uh, Again, just to tell you a few more applications, ceramic coolers, again, how many of you are aware of it, I don't know. So ceramic coolers are very relevant in modern applications because they can be electrically insulating, but it can have very high thermal conductivity. Of course, choice of the right metal becomes very important. So ceramic coolers and ceramic heat sinks for electric mobility is a modern choice. In fact, I will show you another example where such ceramic heat sinks are manufactured, and which is not only used for automotive applications but also in electronics. For example, wherever you think that we can replace metallic materials which obviously has high thermal conductivity, wherever you want to replace it with ceramics, we are looking at long-term stability, we are looking at very harsh applications, and at the same time can give more or less same results as a metallic material with high thermal conductivity would have given us. So ceramic coolers and structural ceramic coolers are a reality as on today. But if you look at this application, this is a ceramic heat sink. Very nice application. I really like this application. I show this many times because we have all seen, I mean, I'm sure most of you would have seen heat sinks made of copper based materials. But I don't know how many of you have seen alumina and aluminum nitride based heat sinks like this, and print even electronics over that. So this is a very nice application because you are completely replacing it with a ceramic, and use a ceramic which has reasonably high thermal conductivity. For instance, aluminum nitride has a reasonably high thermal conductivity and can be a very good competitor to copper. But then if you look at the geometry, you know, to design a heat sink, you require a very high surface area because you need to dissipate heat. That's the engineering part of it. And the material part of it is it has to have very high thermal conductivity. Now, having a high thermal conductivity, you can always talk to a very good ceramic scientist and he can tell you. But to make a ceramic heat sink like this with very high surface area becomes a challenge. And that is where I feel having a route such as additive manufacturing could be of very much helpful, because manufacturing such ceramic heat sinks via other conventional methods and machining can be a problem. And I think this is where additive manufacturing can be a very useful technique. Another example, again, I have started to use this example in recent times because I was very much impressed. I think most of you who are aware of bearings might have seen bearings with steel balls or steel rollers. And when I first came across this a couple of years back, that completely these steel rollers and steel balls are completely replaced with ceramic balls and ceramic rollers in bearings, I was very mesmerized because I was very impressed with the use of these manufacturing of such silicon nitride balls and silicon nitride rollers in bearings. In fact, I continuously bothered somebody in Europe to send this to me, and finally he sent it to me, and I just wanted to show this to you because, and I'm sure you would be, don't drop it. If you drop it, I'll keep you here for a PhD. So so this is a silicon nitride ball manufactured by one of the European companies, primarily meant for using in bearings. And replacing completely steel balls, because steel balls, if you look at steel as if you want to use steel balls in bearings, steel, you look at the density of steel and look at the density of silicon nitride. Silicon nitride density is around 3 gram per cc, and your steel has a density at least more than 2 times the density of silicon nitride. So you are already, or rather we are already looking at use of such ceramics in such load bearing application. It's a load bearing application. So now you can see, can we manufacture such kind of components using additive manufacturing is a challenge. But nevertheless, you should know that it is such applications are possible. Such applications are possible and very much relevant in modern times. This is again a silicon nitride substrate. Again, I was very much happy to see this because now silicon nitride substrates are used as power modules again for electric vehicles, and people would like to manufacture them with almost no defects. This manufacturability of such silicon nitride substrate may not be so complicated and may not require additive manufacturing, but nevertheless, you must know that such kind of applications are now a common thing. Again, there are many other applications like in automotive applications. I am very much impressed with this brake disc using carbon fiber reinforced silicon carbide composite. Obviously, this will such a kind of a brake disc will reduce the weight to a large extent. In fact, if you are very much interested in automobiles and Ferrari, for instance, all the high-speed racing cars use these kind of brake discs. In fact, what we have, you are all from Chennai. I think many of you are from Chennai. You might have heard of this company, Brakes India Limited. So Brakes India Limited uses cast iron. So obviously cast iron blocks are much more heavier. And then people are using these ceramic brake discs to completely, it's for lightweighting. Basically have a car which is extremely light and can go at extremely high speeds. And similarly, for example, you can see honeycomb, corduroy, and so on with catalyst support to prevent and convert all the NOx gases or the exhaust gases into cleaner emissions. In all these cases, I'm not saying that all these applications can eventually be manufactured only by additive manufacturing route, but at least these applications are already in vogue. That means these are applications that are already in vogue, may not be extensively used, but people are already using them. And one could think of additive manufacturing routes, or at least think of newer routes to manufacture them. And this is another important application for combustion chamber, for rocket engines made up of highly refractory materials, including CMCs. And of course, these are relatively easier to manufacture using additive manufacturing route. But again, these are ceramics meant for extremely harsh applications. And of course, you can use additive manufacturing as a route to make them. Okay. I talked about very complex and very high profile, hi-fi applications related to automotive, aerospace, and so on. But additive manufacturing route is also very much in vogue for luxury and jewelry components. In fact, in one of the lectures, I even saw Paulo showing jewelry being manufactured using additive manufacturing. And this is something that I saw first time maybe a couple of years back when I was in France, where one of the companies which manufactures 3D printing machines, he had put up a stall where he was trying to manufacture ceramic cases and ceramic straps using 3D printing technique. And that was the first time I really got really impressed because I thought it's very nice. And that was a time when we first purchased I thought of purchasing a fused filament based 3D printer in our lab. I think some of you saw that yesterday. So making this is again not so easy. Very few people can make such kind of ceramic watches, but nevertheless, it's a very nice niche industry. And ceramic watch industry is a very niche industry. I don't know how many of you know a Titan ceramic watch may cost anything between 25 to 30,000 rupees. And there are Swiss brands and other European brands of ceramic watches which can be as costly as 5 lakhs to 10 lakhs. If you have money and don't know how to spend it, these are some of the avenues to really look at. But anyway, so I was so much interested in this that when we first procured this 3D printer, I think one of the tasks that we took was, can we make a case of a ceramic case for a watch? And also we tried to see, can we surface modify and color it, because people also would like to use colored ceramic watches, and these are very nice to wear, and they can withstand harsh applications. They in highly humid conditions like Chennai, you don't have to face removal of the plating and so on. So they certainly have nice applications. Additive manufacturing can be a potential route. But if you look at my previous slide, I had put one comment. I don't know if you noticed it. I said commercialization depends on industry acceptance. You may come up with a new route, but the new route should be accepted by the industry. And to be honest with you, in fact, when I talk to the ceramic, the 3D printing machine manufacturer in France, from whom we have actually purchased one of the printers, and I asked him whether this kind of a 3D printing method is currently accepted by industry. He said, no, still not. We are not able to convince the industry to use 3D printed ceramic watch. So although ceramic watches are not really load bearing, I think industry is still not accepting. So now you can imagine that new manufacturing methods are nice, but to really come to industry acceptance, I think it's not so easy to convince the industry. But so that is where I think, I just wanted to bring a context towards why are we, to make industry accept what you make, it's very, very important to convince the industry, particularly in the domain of ceramics, that it is mechanically stable. And when I say mechanically stable, we should have some idea about its deformation. We should have some idea about its microstructures and defects, and some idea about its fracture toughness. Unlike metallic materials whose fracture toughness is typically more than 50 MPa root meter, most of the ceramics have fracture toughness less than 10 MPa root meter. That is why they break. You drop it, it breaks. And therefore, please don't drop that silicon nitride ball. They said that it will not break, but I don't want to break right in front of my eyes. So it's very, very important to actually understand the deformation behavior. And deformation is a very elaborate issue. For example, when we talk of deformation, it could be deformation primarily because of mechanical load. It could be thermal load. Even I would call even thermal load as causing deformation, which we categorize them as thermal stresses causing issues. It could be a combination of thermal and mechanical, and also sometimes environmental factors also affecting the deformation response of materials. For example, if you have a crack in a material and if it is exposed to highly humid conditions, you will see how it can, the crack can slowly grow if there is any presence of tensile stress in such components. And obviously, on the other hand, we are looking at what kind of application. If the applications have to be primarily at room temperature, we are only interested in room temperature deformation. If the applications are intended for high temperatures, then you have to do high temperature mechanical testing. And primarily, our interest is to see whatever is the application of that component. It could be ceramic, metal, whatever. We need to see whether, and we need to test under those conditions and really validate them. And particularly for ceramic materials, it becomes very important for us to understand its fracture characteristics. So we need to get a comprehensive idea about crack initiation, propagation, how to mitigate that. And that becomes more relevant in ceramics, because metals we don't worry, because metals can plastically deform. And any crack in a metal, it's not a big problem. But any crack in a ceramic is a problem. Or any flaw is a problem in ceramics. So therefore, mechanical testing becomes very important. As I told you, mechanical testing cannot change just because you are using a new manufacturing technique. So you may have heard from Professor Paulo very nice, interesting talks on very new methodologies in additive manufacturing of ceramics, but testing cannot change. So I will have to again go through the same mechanical testing which you might have studied even in your undergraduate studies. But it's better to go through and we can discuss if there are still some questions. Now, the biggest challenge is, I have realized, people don't know what kind of testing has to be done. Because everybody thinks that when you say testing, you do tension and compression. It's not like that. It's not as simple as that. When you do mechanical testing and you want to evaluate the mechanical stability of the component, you have to actually look at what is the intended function and what is the intended application. That will determine what kind of mechanical testing you have to do. So that is why it's very, very important to first understand what kind of mechanical testing you have to first do based on the application. So for that, what you need to understand is, you need to understand under applications or under service conditions, what kind of state of stress these components might be subjected to. So I'll take the examples of metallic materials because it's easy to explain with metallic materials, because ceramics have not as many diverse applications as metallic alloys. So I take examples of metallic materials to drive the concept, but that can be extended to ceramics as well. I give you a few examples which are in real life examples. I don't know how many of you have used ski lift. If you have been to northern parts of India, maybe you would have done that, or if you have been in Europe, you would have used the ski lifts. And if you look at this cable, the cable is usually in a ski lift is subjected to a tensile mode of stress because they are always in tension. And if you look at this drive shaft, the drive shaft is always in shear. So if the first job of an engineer is to first find out in application or during service condition what kind of stress state each of these components are subjected to. I many times ask students in the class. For example, if the fan is rotating at a very high speed, I ask them what is the state of stress in the blade of that fan, for instance. Or for example, if he's sitting on the chair, I would like to know what is the state of stress those pipes which actually withstand his weight. So one should be able to quickly tell what is the state of stress in any component which is subjected to a certain application. In fact, once I asked the student, what is the state of stress in the belt that you're wearing? He suddenly panicked. So what I meant to say is that it's very important to understand what is the state of stress that any component is subjected to in service conditions. So when you do that, when you understand that, then you know what is the kind of testing that you will have to use. For instance, if this cable is subjected to in service, always a tensile load, then obviously the material that you are going to use there should be subjected to a uniaxial tensile test. And it's uniaxial, and the cable will be always has a very high aspect ratio and will always be subjected to a uniaxial stress state, and therefore it's mandatory to test such materials which will go into the as a cable in such ski lifts to be subjected to a uniaxial testing condition and design it for uniaxial load conditions. And in this specific case, in a drive shaft, since it's subjected to a torque, it is always subjected to shear, and therefore you need to conduct a shear test. This is one such example. I think some of you might have seen this. You might have been in such kind of giant wheels. So all the spokes here and these rods which hold this, they're all subjected to tension. And because they're subjected to tension, these particular elements or components, we have to test only in uniaxial tension. I'm just giving you an example. Now this has to do with metallic materials. Now I can give you more such real life examples. For example, this is a tie rod in railways. Whenever you go in a train, just look outside the window, you will see a tie rod which connects two components. A tie rod is always subjected to a tension. So therefore, if you want to choose a material, if you want to design a tie rod, you always have to first subject material that you use for tie rod under uniaxial tensile conditions, and then only you can use them. Now that I gave an example, I have given all examples till now which have to do with metallic materials. Now if you just move to a little bit more high profile application like a gas turbine. Many of you take a flight, and when you take a flight, the heart of any flight is basically a gas turbine, and the gas turbine has this gas turbine blades which are rotating at high speeds, and if they don't work, you cannot really fly. And these gas turbine blades in modern times are used, they use the thermal barrier zirconia based coatings, and that is why you can actually go at very high speeds. Go at high temperatures. The turbine can operate at high temperatures. Now the relevance comes here. The ceramic relevance comes here because you have a metallic material over which you have a zirconia coating, a ceramic, and they are rotating at high speeds. And when they are rotating at high speeds, that means the turbine blade is actually subjected to a state of tensile stress because it's the centrifugal loads that are acting on the turbine blades. Which means if the turbine blade is subjected to a tensile stress, then the coating, the zirconia coating on that will also be subjected to a tensile stress. So therefore, zirconia, when you coat this material, if you want to check the long-term reliability of zirconia coatings, obviously you have to carry out a tensile test on such zirconia material, which is meant for that particular application. You understand? So it's very, very important to find out what is the final application it will go to and determine that kind of testing to be done. I just give you an example of why zirconia has to be subjected to tensile testing and that to uniaxial tensile testing for zirconia going into a turbine blade. But if I think of a zirconia tooth, for example, I have replaced one of my, I had a root canal treatment and I have replaced this with a zirconia cap. You know that you can always have a ceramic tooth cap, and that is usually made up of tetragonal zirconia because it is quite tough. But zirconia tooth, what has gone into my mouth, I don't subject it to a tensile test because I always chew it and I always subject them to a compression test. So the zirconia that goes into my tooth, I have to always do a compression test to qualify that material. So you just don't decide testing techniques just like that. You have to decide the testing technique depending on what is the final application? I don't know how many of you have seen this high tension cables and you might have seen these insulators outside. For example, this porcelain suspension insulator string is always under tension, and therefore such porcelain insulators will always have to be subjected to tension. Now and evaluate the properties. Now if you look at it, it's not so easy. Because if you look at this, the shape is not just cylindrical. The shape is complex. And you cannot just take a cylindrical porcelain rod and then do a tensile test and say, this is my tensile strength. It need not be. Because ultimately in use, it will not go as a cylindrical rod. It goes as such kind of ceramic disc, which means you cannot translate the tensile strength that you calculate for a porcelain rod to this directly, because it is not used as a rod. It is used as ceramic disc. So which means that shape will also matter. Now, can we do all this all the time? Can we do such a mechanical testing? No, not possible, because it's very difficult to manufacture that kind of a component and do tensile testing. So what generally design engineers do is they add a factor of safety and make sure that you can still go ahead, because you may not have been able to perform tensile tests on actual shaped specimens. So therefore you do a factor of safety and go ahead and do your design calculations. So I just talked to you about the design part and give you a few examples for tension. But most of the ceramic components are not really subjected to tension, because I gave you a few examples, but most of the ceramic components are good in compression, and they are usually weak in tension and good in compression, and therefore generally whenever you have to deal with ceramics, we are mostly interested in carrying out compression tests, and we do compression testing. And I'm not talking too much about the basics because I assume that you know this. So we do compression testing, calculate the compression strength, and then tell, okay, this is the compression strength of the sample. Fine. But these are samples which I took where they are of uniform shape and size. But in reality, you will not have uniform shape and size of components. For example, if I have, in fact, I was talking to a professor in engineering design 3-4 days back. She was asking us if we can make a shell like a skull kind of thing, which she said, can you make with a 3D printed part? Yes, we can. Let's say we try to make it and we are successful in that. But then a skull type of or hemispherical kind of a shell will not be subjected to a uniaxial loading condition. So you must understand, for example, if you take a cylinder, if I make a ceramic cylinder like this, I cannot do a simple uniaxial tensile test and use those properties for designing a ceramic, although I'm not showing a ceramic cylinder, but the concept is the same. You cannot simply do a uniaxial test and do that. Now, if you look at this, in this particular example I'm giving you, because this is something that most of you have seen. If you may have seen a gas cylinder at home, a gas cylinder is a internally pressurized cylinder, and because of the internal pressure, the wall is always subjected to a biaxial tension. So you cannot do a uniaxial tension test on the material used for cylinder and design the cylinder. Not possible. That is not correct. So you have to do a biaxial tension test to actually determine the properties. But many people don't know this, and they simply do a uniaxial test and they think that uniaxial test solves every problem, but that's not really correct. So you have to find out what kind of loading condition and what is the state of stress the material is subjected to, and then decide the testing techniques. Here, because it's an internally pressurized cylinder, obviously the material of the cylinder is subjected to a biaxial tension. So even in reality, when you want to do a tension, you don't do a uniaxial tension, but go for a biaxial tension. But I'm more or less sure at least more than 90-95% of you might not know how biaxial tension is done. So I think we have one lab session today. You can have a look at it. We have designed a customized setup to actually do biaxial tension, both, of course, for metals we use for metals, but in principle can be used for ceramics as well. And the last one is a simple example of a hydrostatic compression for the sake of completion. Anything which for example, if you are underwater, you are always under hydrostatic compression. Not ceramics, I don't really consider too much of examples are there for ceramics under hydrostatic compression, but you must know that is one of the state of stress. And I'm sure, I don't know, many of you might have seen such kind of cylinders. They are all subjected to biaxial tension. I don't know how many of you know this kind of it's a It's a swimming pool dive board, but typically meant for resilience. That is, it has to absorb energy and give back energy. Although in a dive board, nobody uses ceramic, but there are applications where ceramics are used. For example, there are sensors, sensing devices where ceramic sensors are used, where it is subjected to uniaxial bending like this, and it requires some level of flexibility and compliance. And you must know, if there is such an application, what is that we are dealing with? We are dealing with something called resilience, that is ability to absorb energy and give back. So the reason why I said I'm not giving a lot of ceramic example, but other example is that this is easy to realize. But there are ceramic examples as well, but whatever you see here can be directly translated to ceramic examples. So this is a uniaxial flexure condition, and it's a dive board. So that means if somebody stands here and puts pressure and then jumps, he basically gets all that energy that he had transferred to the dive board back so that he can jump very well. So that is what is called resilience. If you take a tennis ball and then drop it, if it jumps back, bounces back, that means it has resilience. It has the ability to absorb energy and give back. And that kind of application is very important in ceramics, particularly for some of the sensing applications where ceramics are used. So anyway, to summarize, you need to know what you are measuring. You need to know what kind of testing technique. You need to know what kind of loading you need to do to basically get the most important properties of materials like stiffness, strength, toughness, ductility, and so on. Obviously, ductility is not a very important topic for ceramics, but you need to know what we are doing it. So I just go ahead quickly because it's something that you know. So because tension test is a very common thing that you even do in your undergraduate studies. But the biggest problem that I have seen is that whether when you do such a testing, are you doing it correctly? That is the biggest problem. Anybody can do a test, but are you doing it correctly? The biggest challenge is when you're doing tensile test, I always ask what was the strain rate that you have used. And the typical strain rate that you have to use is something like around 10 power minus 4 per second. If you don't do that, you are not really getting the right result. And again, the biggest challenge is when somebody does a tensile test, I ask them, did you do compliance correction? And many of them are like blinking. They don't know that what is compliance correction. Compliance correction is all about any machine will have its own stiffness. So whatever data that you get from the machine, is it exactly the data that you get from the material, or does it involve contribution from the machine also? Has to be taken care of. Whatever contribution comes from the machine stiffness, that has to be removed. That is what is called compliance correction. So irrespective of tension or compression or bending, whatever testing technique you use, you always have to do compliance correction. Compliance correction is nothing but removal of the instrument contribution to the data that you get from the material. So once you remove that, then you get whatever data that you get is purely because of the material contribution. So compliance correction is very important. And the other thing that I also have to tell is, I think as engineers, many times, many of them do not have an idea of what kind of testing machine I have to use. And this, in fact, recently in Indian Ceramic Society meeting in IIT Bombay, one professor actually from IIT Roorkela highlighted it, which I accept, because if you ask any kind of measure, like what is the machine capacity that you would like, many people don't have an idea. What is the machine capacity that I have to use? For example, if I want to do tensile testing or compression testing, I can get a 1 kilonewton machine, I can get a 5 kilonewton machine, I can get a 10 kilonewton machine, I can also get a, 100 kilonewton machine. But you must know what is the capacity of the machine that I need. And that is determined by the kind of samples that you work on, the kind of materials that you work on, the size and shape of the samples that you work on. So unless you have that, I think then we are all talking in air. You are not really an engineer. You don't know what to do. So it's very, very important that all of these are very important, although it's a very, very trivial thing, something taught in the first year engineering course. But I think this is something that not many people have realized. And it's very, very important to understand what should be my strain rate. This should be approximately my strain rate. How do I choose the capacity of the machine? That depends on the material, that depends on the size. All that will determine what should be the capacity of the machine. And of course, one thing that everybody misses is compliance correction. Unless you do compliance correction, the mechanical data that you get is not completely correct. Of course, for people who are into mechanical testing will know, but people who are not generally doing mechanical testing regularly may not know. But when you do mechanical testing, For that matter, many other kinds of testing also. But in mechanical testing in particular, you have to always follow standards. You cannot simply take any shaped specimen and do whatever you want, of any size, and do whatever you want. There are ASTM standards which you have to follow. For example, if you have to make a dog bone shaped specimen to do a tensile test, you have to do a dog bone shaped specimen. If the gauge length is fixed to a certain level, you have to have a sample of that kind. If you cannot, for example, in ceramic samples, it's very difficult to always follow ASTM standards. Then you have to do a large number of tests to validate it. Otherwise, people will not accept your data. In metallic materials, it may be easy and it is well established. In ceramic samples, it's not always well established. You may not have ASTM standards to follow. And then when you do not have ASTM standards to follow, you have to do lots of tests. If you're not following standard specimens size, then you have to perform lots of tests, validate the data, and confirm to people and community that you have actually generated a lot of data, and therefore the data is reliable. And other issues are mostly, how to handle it. For example, this is again something that I have noticed more in India. I mean, not to compare how it is done in other countries, but it's important to know. For example, many of them do not take care of, when they do even a simple tensile test, they do not take care of fixing the samples properly. It's very, very important. If you are very much, if you think that getting data, correct data is very important, fixing it properly and really making sure that there are no slippage and so on, it's very important to do this fixing properly so that you get whatever data that you get is accurate enough. Now, these are some very basic things. A technician should do that, but nevertheless, we should be aware of it. And the biggest challenge is to measure strain, because when you do a typical tensile test, you need to measure strain. And for metallic materials, again, it's not a problem. But ceramic samples, it's a problem. Why? Because the strain in ceramic sample is very low. In fact, 0.5% is a failure strain of many ceramic materials. That means you are dealing with extremely small strains. And when you have very small strain, your ability to measure strain should be very, very accurate. Otherwise, you will not be able to get correct data. And for that, of course, you have strain gauges. People use contact mode strain gauges. And you fix the strain gauges and then measure. Again, easy to do for metallic materials and not so easy to do for ceramic samples. But in modern times, people use laser extensometer. So you can use a laser extensometer to really see the change in length because of the application of tensile load. That's a non-contact mode. And typically also very much relevant, for example, if you have wires. And nowadays, one of the challenging topics in ceramic science is making ceramic fibers. So when you want to test ceramic fibers, in fact, both fixing as well as measuring tensile length, change in length becomes a very challenging thing. For example, we work on ceramic fibers. We are interested to develop long ceramic fibers and filaments. It is not very easy. In fact, we have tried with glass fibers and so on, not so easy. So when you're dealing with extremely brittle materials, when you're dealing with glass, ceramic, fibers and so on, you have to know how to fix these samples. So it becomes so critical, which many of them think that it's a very trivial thing, fixing what is there in that. No, it's not so easy when you're dealing with ceramics and glass samples, and particularly when you're dealing with fibers. So if you not a problem with metallic wires, but definitely a problem with ceramic fibers. So if you are able to fix it well and measure the strain very well, and ceramics do show very limited strain, but you should be able to measure such kind of strain, then fantastic. And it is a laser extensometer which is now used. And in modern times, people are also using digital image correlation technique. I am not sure how many of you have heard. So basically, you make a speckle pattern. You take this sample, whatever it may be, ceramic, metal, whatever. Then you apply a white paint and then put a black dot of speckle pattern, a random set of patterns, and then use high resolution, high speed cameras to capture the relative displacement of all these points so that you get a complete strain contour. So unlike strain gauges and unlike laser extensometer, when you use digital image correlation technique, you get a complete strain contour map. You get a complete information about the strain over that entire surface. You can get that information. So that non-contact mode also helps us to really get away with the strain gauge problem, because strain gauge, what happens is that it tends to peel off when deformation takes place and so on. So therefore, non-contact mode is a fantastic thing. Again, easy to come and give a lecture, but not so easy, because we have done with digital image correlation technique we have used for ceramic samples, not so easy to particularly capture strain in the elastic region. So why I'm saying this is that what many people think that mechanical testing is a very easy thing. It's not easy. If you want to get reliable data and if you want to get credible data. And we have seen, in fact, one of my former students really struggled to get elastic strain, which is extremely small in ceramics, using digital image correlation technique. So, challenge. Yeah. So, I mean, this is the kind of challenges that we actually face. And for people to get a rough idea of where we stand, this is a Young's modulus as a function of strength. So obviously, technical ceramics will be on the right hand side, top corner, because their Young's modulus is also high and even strengths are high. In fact, the typical compression strengths of ceramic samples will always go up to almost a few gigapascals, and Young's modulus is always in the order of around gigapascals. And if you look at some of the polymer based samples, they are on the other side of the spectrum. So we are always dealing with materials of this level, which means when you are talking about strengths close to a gigapascal, and when you're talking about Young's modulus in the order of several gigapascals, then unless you have ability to measure them accurately, then you fail. So that is the reason why you need to have a rough idea of its strength and Young's modulus, so that you can deal with such kind of machines. I think I already talked about resilience, because resilience is all about how much energy it can absorb and give back. So this is a very important design concept. I actually show this because you can have the same Young's modulus but different resilience. That is, I can take two different materials with the same Young's modulus, but ability to absorb energy and give back can be very much different. And I used to show this example particularly in the context of bulk metallic glasses, which when I was a student, bulk metallic glasses used to be like people used to make ribbons. And now bulk metallic glasses are now used in tennis rackets. They are used for energy absorption applications and so on, because bulk metallic glasses have very high strength and as well as very high ability to absorb energy and give back. And when any material can absorb energy and give back, that means that is a highly resilient material, and that you can calculate very easily. The area under the elastic stress strain region is actually a measure of how much energy it can absorb and give back. That is called resilience, and that's a very important one, particularly when you are dealing with I think one example that I can give you immediately, which you can relate, is spring. A spring is something that can take load and give back. But most of you have seen steel springs. But how many of you have seen glass springs? How many of you have seen ceramic springs? In fact, glass springs and ceramic springs are really relevant, particularly when you're dealing with, again, ability to absorb energy and give back, and at the same time being light. Glass and ceramic springs really outperform even steel springs, which you may not know. This is, when you're dealing with macro size samples and so on. But many times in ceramic samples, we also deal with very small sized specimens and so on. And then you really have to go for micro tensile tests or micro scale machines. In fact, I already told you that you first need to know what are the kind of samples you deal with, so that you can accordingly select the capacity of the machine. In this case, the capacity of this machine is something like, which varies between 0.001 to around 250 newtons. It's from a company called MTS. I mean, I've put MTS, but there are other companies also which can provide you this. And these kind of testing machines are typically used for maybe thin films where you require extremely low loads, or even materials which you may use for biomedical devices, some of the electronics you want to test them, and so on. But anyway, coming back to compression tests, which is more relevant for ceramic samples. It's not so easy, again, because ceramic samples are not so easy to manufacture in a certain way. And so generally, there is more, I would say, leeway and leverage on the shape and size of the samples. But we use to test the strength and get a typical deformation response for ceramic materials, we always use compression tests. But we use typically the same strain rate, like in the order of around 10 power minus 4 per second, and generate the load displacement curve. And for that matter, all brittle materials, you can do that. And as I said, when you use when you use compression test, we also look at the application. For example, spring is an application typically used for compression, and therefore people would like to measure the deformation behavior of springs in compression. This could be metallic. This could also be ceramic, by the way. And again, look at the application, decide the testing technique to generate the data. So this just to give you an example. You never do a compression test for tensile samples, because if you do a compression test for if you do a compression test for a ductile sample, it typically tends to barrel, and you don't get useful data. On the other hand, if you do a compression test for a highly brittle material or such as ceramics, typically it fails in shear at 45 degrees. You get good data, and then you can actually get compression strength reasonably accurately, and then you can understand the deformation response. So typically compression tests are used for any brittle material, including cast iron, which is quite brittle, and of course for all the ceramic samples. The only thing that you must know in compression testing is that you must have the compression coupons in such a way that it doesn't buckle and it doesn't fail in a mode that it should not be. For example, we would like the compression samples to usually shear. So this is the kind of L by D ratio you would like to have. So you typically have compression tests done based on the L by D ratio so that it doesn't buckle, and typically you have to ensure that it fails by shear and not by anything else. So this is something that you must know. And another important testing technique which we typically use for brittle materials or even for ductile materials is bending. And bending test is one of the very important qualifying criteria for many of the applications in ceramics. Of course, done for metals as well, but definitely for ceramics. And I have this question. Many times I do ask this question because people report bending strength tests data many times here and there. But what kind of bending test would you do? And you would have seen in reality people doing 3-point bend test. You also see people doing 4-point bend test. But you must know what is that you are getting from them. 3-point bend test also people report. People also do 4-point bend test. I know a lot of ceramic community who uses only 3-point bend. I also know a lot of people who also use 4-point bend. The biggest challenge in ceramic community is when they do this mechanical testing, most of the ceramic community comes with either material science background or comes with a chemistry background. And because of that reason, they do not really worry too much about what kind of testing technique to be used, possibly because they do not have that kind of a strong idea. But it's very important for us because this will determine a lot of things. Which one to choose? You have 3-point bending, 4-point bending. But if you have come from engineering discipline, you will know that typically, I mean, just to give you an idea, this is a 3-point bend test. So you have a sample, they are supported by 2 points at the bottom, and you have a central loading point. And what should be the distance and so on is determined as per ASTM standards. And this is a 4-point bend setup, again supported on 2 points, and you have 2 loading points, which is in 4-point bending. And what should be the span, what should be the loading point distance, all of them are specified as per ASTM standards. So you have to follow ASTM standards. If you cannot fabricate your ceramic samples as per ASTM standards, one of the possibly permitted methods would be to simply downscale the same thing. Keep the ratio same, but downscale it and then do it if you cannot fabricate bigger size samples as per ASTM standards. So this is a 3-point bend, that's a 4-point bend. I don't know which one you have seen in life, but people use both. But what is actually really correct? What gives you accurate description of this uniaxial bending strength? And this question I usually ask many students in the class because they would have done their first year engineering course. I wanted to check how much they actually relate to what they have studied in their first year engineering, but I see that not many people can relate. Please note that when you do such a bend strength test, actually what gives you an accurate description is not 3-point bend, it's always 4-point bend. The reason is very simple. This is something that everybody learns in first year engineering course, but nobody takes it forward and keeps it in their mind. The reason why actually 3-point bend is not good and 4-point bend strength is good is simply because you have a constant bending moment between the loading spans in a 4-point bend test, which is not the case in 3-point bend. In a 3-point bend, if you take your, I don't know how many of you are from engineering departments here. In your first year course, typically you have two engineering courses. One is engineering mechanics, the other one is strength of materials. And if you have studied this course, both these subjects properly, you would have learned this bending moment diagram and shear force diagrams. I don't know how many of you still remember. And this bending moment diagram, what you see here, will clearly say that it has a constant bending moment and there's no shear between the loading points in a 4-point. But that's not the case in 3-point. And therefore, 4-point bend test give you a much more accurate description than a 3-point bend test. And this many people don't realize, and obviously many of the people who come from chemistry may not know. But people who are in engineering should know this, and therefore I always suggest people don't do 3-point bending, do a 4-point bend test because we know what we are dealing with. Yeah. So the real reason is that 4-point bend test actually is used because it is free of shear and you get bending strength data which is actually accurate. This is something that I always emphasize. Don't do 3-point bending. Now, I just want to see if this video still works. If it doesn't work, then fine. Okay, it doesn't work, leave it. Anyway, you have a lab class here. I think they'll show you. We have made a very small testing machine, primarily for ceramic samples to do, compression, bending, and so on. I don't know if that machine is ready. They had assembled everything. Huh? So you can have a look at it. So we have actually made a very small scale testing machine, primarily to deal with small scale samples because when you do additive manufacturing and so on, you can't fabricate big parts and waste. So, and many of them are expensive when you're dealing with ceramics. So we want to make small size samples and then test them. So we have made it, and I want to show you some new results which we have done in our own lab. And now actually I'm coming to some of the mechanical properties that we try to investigate for our own samples done in our own lab. And this is obtained, this is alumina 3D printed using fused filament fabrication. So we have a fused filament 3D printer which some of you might have seen yesterday. So we have used it. So we have 3D printed it and then have skipped all the processes such as chemical debinding, thermal debinding and so on, and just showing you that we have fabricated 3D printed parts from fused filament. I mean, after all the optimization of thermal debinding, chemical debinding and so on, and prepared compression test coupons for mechanical testing. We wanted to do compression mechanical testing using these materials and these coupons. And one thing that I had told my student is not to waste parts because they're expensive. Because when we use fused filament based, it's not cheap, it's expensive. So you generally, when you want to establish a mechanical testing protocol for an additively manufactured component, you don't have to fabricate a complex shape and then test because that is very difficult to even analyze. I mean, you cannot even get useful data. So what I generally suggest as somebody who works on mechanical properties of materials is you simply prepare coupons as we would have done for any other conventional technique. For example, I need to make such a kind of coupon for mechanical testing or for compression testing. I will do the same thing using additive manufacturing. So I told him that, but the only thing that I told him is, please ensure that because you are using fused filament based fabrication, it may not be isotropic. The mechanical properties may not be isotropic. You may have anisotropicity. So I told him that please test both along the printing direction as well as do compression testing in a direction perpendicular to the printing direction. So that is important for me because that will establish what is the kind of anisotropy in mechanical results or in compression data that I would get. So, as material scientists, the first thing that we do is we look at the microstructures because the properties of materials, definitely in metals and more certainly in ceramic materials, directly correlate with the microstructures. And if you look at this is something that I think anybody who has worked in fused filament fabrication would recognize. You can see this interlayer weakened points, including this open spaces that we see in fused filament based ceramic components. These are actually weak points for ceramics, and therefore we really wanted to test, when we do mechanical testing, we wanted to test both in both, as I said, in both printing direction as well as in direction perpendicular to the printing direction. I'm just showing you the microstructure, how it looks like. Of course, they were sintered at various temperatures ranging from 1475 to 1600 degrees Celsius. So therefore, you can see all these which were sintered at various temperatures. But that is not the point. The point is what kind of defects do you still have? That will determine the compression strength values, and it's also again showing you how sintering can change the microstructure in terms of the porosity distribution. You see right from 1475 degrees Celsius to around 1600 degrees Celsius sintering temperature, the pore fraction in the material could change, and that will definitely contribute to the mechanical properties of your, definitely contributes to the tensile properties, relatively less in compression, but do contribute. And you can see that with sintering temperatures, the density goes up, which is not a new thing in ceramics, but that will definitely contribute. And this is something which is very interesting because you can now see this. We have now done mechanical testing both along the, as I said, along the printing direction as well as direction perpendicular to the printing direction. And we have actually plotted the compression strength, and you see a difference. So that means it's not the same. But so long your anisotropy is limited, so long the anisotropy is not so much, then you may get, irrespective of in what direction you test, you may get more or less same result. But you can see even the standard deviation is not well within the error. So it's definitely different. And so what we recently did, which I'm not showing because we are yet to publish this paper, is we are, one of the students gave an idea that whatever pore fraction or whatever interlayer weakness and triangular pores what you saw in the previous slide, he said, why don't we actually heal them with using some precursors? That was done. And actually we removed all those weak points in the material. And then after that we did testing. Actually the properties improved to a large extent, and we are very happy. We have now submitted that those results to the European Ceramic Society so that we see if people find it very interesting. So this is again testing from bending. And again, as I said, our parts are very small and I didn't want to waste too much. And that is exactly the reason why it's very important to make very small scale testing techniques very, it becomes very relevant, because you don't want, mechanical testing is always a destructive testing. You don't want to waste them. So it's always good to have small scale testing techniques so that you get the best properties, or you get the properties of the materials. At the same time, you don't waste. The only issue would be, can I rely on that data? And that is the reason why it's important to carry out large number of tests to prove to the community that this testing technique is a small scale testing technique. What I'm using is a small scale testing technique developed in our own lab. It's a 4-point bending mode. And I've already told you why 4-point bending mode is important. And I have told you, I have justified the 4-point bending strength technique. And now you can see it's a very small sample, 4-point bending mode. And we have actually measured the bending strength in 4-point mode. You can see variation. Of course, it is dependent on the microstructures, because as we sinter at different temperatures, the pore fraction is different. And obviously at higher sintering temperatures, it tends to be little, irrespective of the printing direction, it tends to have more or less close values. But nevertheless, how much it is close depends on how much isotropy or anisotropy is there in the microstructure. One last thing before I close is, in ceramics, it's very, very important to get the Weibull modulus. In ceramics, strength has a statistical variation. You don't get, if I take 5 samples, all of them will not give you the same compression strength data. So strength result. So you always have a statistical variation. And that is why it's always important to get the Weibull modulus. So Weibull modulus gives me an idea of what is the variation in the strength, whether the variation in the strength is narrow or broad. That has to be established. So it's very, very important to understand the Weibull statistics and get a Weibull modulus if I have to trust your data. And typically Weibull modulus for ceramics, at least acceptable value should be at least, I would say 10 and above. We have not got 10. As you see, the highest value we got is around 8.44. Not bad for additive manufactured component, but I would have loved to get more than 10. So higher the Weibull modulus means narrow the strength variation and less sensitive to flaws. Because ceramics are very, very sensitive to flaws. in the samples. More flaws, the possibility and probability of failure is high. And therefore, when you get a higher viable modulus, that means the ceramic microstructure that you have, the manufacturing technique that you have adopted is less sensitive to flaws. I think this is part of the tensile compression and bending story of ceramic parts in general. I have one more, I think maybe 7, 8 slides on fracture. Maybe only go to the last slide in the fracture, that in ceramics, irrespective of the manufacturing technique, these are very important factors that govern things. For example, the chemical environment, the loading rate, all that would, temperature, all that would matter. Similarly, the fracture strength is always a statistical case. There's always a statistical distribution, and that's very important. Therefore, viable modulus becomes important to do. And in ceramics, it's also important that the crystal structure plays a very important role, because that will determine the cleavage planes and what kind of environment that it deals with can govern its fracture behavior. So this is very important. So I have sort of summarized, because ceramics has to do with fracture. It will fracture at some point of time. So you need to understand it very clearly. So I will skip the other basic things. So I will go to the last part, or some part maybe I can quickly talk about the testing. One of the important testing technique that we use in ceramics is to determine the fracture toughness. Because you must know, for example, a glass there has a fracture toughness of less than 1 MPa root meter. So for example, if I throw one stone there, the glass will break, because it's going to break because it has a fracture toughness of 0.5, 0.7, 0.8 MPa root meter. And so therefore it's extremely brittle. And if you take a metal, it has a fracture toughness of more than 50 MPa root meter. And ceramics typically have a fracture toughness anything between 1, 2 MPa root meter to around 15, 20 MPa root meter. A highly tough ceramic microstructure may have a fracture toughness of around 15 to 20 MPa root meter. And the dream of any ceramic scientist is always to improve the fracture toughness. How do I improve the fracture toughness so that it can have real-time application? But for that, you need to quantify it. And quantification requires a methodology. And one of the important methodology is called single edge notch beam. So basically, you have to test the sample like in 4-point bending. So that is why I said if you have a 4-point bend setup, you can not only measure a 4-point bend strength, but you can also measure fracture toughness. Because all that you need to do is that if you don't have this crack, you get 4-point bend strength. If you introduce a crack as per standard, then you apply load to the extent that the crack is going to extend, then you know at what is the load at which the crack is going to extend. That will be the critical load. L is this length and W is the width. D is half the thickness, and that will give you the critical failure stress. And once you know the critical failure stress, you can actually calculate K, because you know what is the critical stress, you know what is the critical crack length, you can calculate what is the fracture toughness. So this is something that you have to, it's an acceptable ASTM standard method, single edge notch beam, and you can do this. So, and that will give you a measure of what is the fracture toughness of material. Whether it is for toughness, or whether it's for fracture toughness or for strength, you have to do at least 5. 5 is still small, but if you can do 10 to 15 tests, then you get a very good estimate of values. So I will skip the other parts and I will directly go to the last one. Ceramics are defect intolerant, unlike metals. So therefore, you have to understand that even a very small defect in ceramics can be a point for failure, initiation of failure, unlike metals. So you have to be very much cautious of that, and more so in additively manufactured parts, but because in additively manufactured parts, you also have to look at flaws and thoroughly check for defects. Anisotropy in microstructures. Depending on the manufacturing technique, it's important to look at the anisotropic character, and that will determine, and ceramics tend to be weak at sharp discontinuities, so you need to be careful of that. And I think additive manufacturing, although in ceramics, it is in vogue for about a few years. I think mechanical testing protocols are still not established. I think more tests have to be done really to believe that these are the properties and to establish them for real-time applications. So single edge notch beam, these are standards. Actually, you look at any ASTM standards, you will know what should be the crack length. I have not mentioned, but there are standards which clearly say what should be the dimensions of the specimen. for that dimension of the specimen, what is the crack length that you have to produce. And typically, again, all these are experiment. I think you should be very good at hands, because when you create a notch, you need an atomistically sharp crack, and therefore you have to use a very thin blade so that you create an atomistically sharp crack and create exactly that length of crack. So it's very, very important to do that. Otherwise, and when you do that, you should not create other artifacts. You should not create maybe additional defects or additional cracks here and there. So it's a very carefully to be carefully done. Follow that and apply load in 4-point bend and keep monitoring the load, and there'll be some critical load at which the crack would start. That C will not be C anymore, C plus delta C. And when it becomes C plus delta C, then that C becomes your equilibrium crack length. And that sigma F, that sigma A which you applied, will become sigma F. I don't know if you understood what I'm saying. When you have a crack length, you have to keep applying load, and at some load, the C will give up and it will proceed further. And immediately you can check that in the load, and that becomes your critical load, sigma A, and from that you can calculate sigma F. And that C will become your critical crack length. And then for that critical crack length and for that sigma F, you can calculate K1C. And that is your fracture toughness in single edge notch beam. And this is an easily doable experiment, because all that you need to have is a 4-point bend setup, and you need a compression machine which can apply compression load. Keep the entire 4-point bend setup, apply load, and then you can find out what is the fracture toughness. Do more than at least 5-6 samples. If you can do 10-15, all the better, to get reliable data. Calculate fracture toughness in MPa root meter with a standard deviation. And the standard deviation will tell me whether you have done properly or not. For example, for a material with a fracture toughness of 2 MPa root meter, if you show me plus or minus 1, then I will say your experiments are wrong. For a material which has fracture toughness of 2 MPa root meter, I would expect your standard deviation to be not more than 0.2 MPa root meter. For a sample which has a fracture toughness of 10 MPa root meter, plus or minus 1 or 2 is fine. Okay, so the standard deviation will tell me to what extent you have done your experiments correctly or not.